Okay. All right. So I'm going to start thermodynamics, which I told you already is a study of energy and energy flow. Where is the energy going? And of course, we're interested in chemical systems. So we'll start by talking about energy, but the first type of energy that I want to talk about is internal energy, which you'll see in some books has a symbol E, but our book uses a symbol U. Okay. And the first law has to do with changes in internal energy, which is delta U, which we'll be getting to. Okay, so internal energy. So what does it even mean? So this is the sum of all the potential energy and all the kinetic energy of a system. So what are the types of potential and kinetic energy that a system can have? So let's suppose we're talking about, say, a diatomic molecule. So it has kinetic energy. It has what we call translational kinetic energy. Great. Okay. So translational kinetic energy, is just like linear motion. You know, you have a molecule here and the molecule moves there. All right. And of course, we know that there are 3 different directions. It has 3 directions, 3 degrees of freedom for linear motion. So if we had a monatomic gas, so just a single atom, that's the only kind of kinetic energy that it can have. In fact, it's the only kind of energy it has, if you don't count, you know, energies that physicists would count, like nuclear energy and things like that. So to us, for a monatomic gas, this is the only kind of kinetic energy. And it's really the only energy. Because a monatomic gas can't vibrate, it can't rotate, it just can't do any of those things. Okay, so so that's the first type of energy, this translational energy, translational kinetic energy. But if we have a diatomic, it can also rotate. So we have rotational kinetic energy. And a diatomic, okay, it can rotate different ways. It could rotate like this. So it would be about this axis, sticking out where that dot is. Or it could rotate like this, where it's going, one side is going in and one side is coming out. Okay. But if it rotates like this, see, when you rotate this way, the first way, the positions of those atoms are moving. The nuclei are moving and the electrons are keeping up, right? Actually, but anyway, in this one, you also have the atoms are moving. One is going in, one's going out. But if you rotate about this axis here, there are no atoms that are really moving. They're not moving position. So this is not considered a type of rotation. So we say that there are 2 independent degrees of freedom for rotation of a diatomic. Okay. Yeah. And then we have vibrational kinetic energy. But actually vibration is a little more complicated. So here's a diatomic. You can pretend it has something like a spring. It doesn't have a spring, but it does. There are vibrations, and it's like the pull and pull of the electrons in the nuclei kind of mimic a spring action. So we can think about it as having a spring. And when you have a spring, you know, you have an equilibrium position. And then if you pull the spring out, okay, you stretch it. I would really rather have drawn this symmetrically, but of course I didn't. There we go. Okay, so now it's in its stretched position. So here at equilibrium, right, so if you pull it out, you have a high potential energy. But remember, if that spring is really vibrating, when it's at its maximum position, it stops. It has 0 kinetic energy at the maximum position. Okay, then, you know, so it stops here. We call these classical turning points, right? And then it gets scrunched. Okay, so it's moving from this position. It's going back through the equilibrium position and then to the scrunched position. So this is the minimum separation. Okay, so, and it's moving from here to eventually getting here, and then it's going to go back out again, right? So here at equilibrium, it actually is moving the fastest. It has a high kinetic energy, but this is our 0 of potential energy. And then when it's scrunched, again, it has the maximum potential energy and 0 kinetic energy as it stops and goes the other way, okay? So we basically have potential energy and kinetic energy in equal parts, really. So we get some potential energy that contributes to the internal energy, and we get some kinetic energy that also contributes to the internal energy, and that's all we really care about. If you have a monatomic, then you have no chance for vibration. You have no vibrational energy, okay? But you do have kinetic energy and potential energy of a vibrating molecule, which leads to a contribution to the internal energy. So that's the third. And now there's electronic energy. And electronic energy, that means that, you know, you could have a molecule that can be in an excited state. And maybe one of its electrons went from a pi to a pi star. So you'd have to count that. But here's the thing. The thing is, at room temperature, most molecules are in the ground state. And you'd have to give them a photon to excite them to a pi star, for example, an electron to a pi star state. So at room temperature, most molecules are in their ground electronic states. So this is not important to us. And here's another thing I'd like to mention, and that is potential energy due to intermolecular attractions. Okay, so when you get attractions, it decreases the internal energy. It decreases the energy. We can think of it as potential energy. And that's because it's more stable, right? When you have, you know, attractive forces. It would be extremely difficult to sum up all of these contributions. Okay. Another thing is that I've left out the most important thing. And that is what is the biggest contribution to potential energy that I haven't even mentioned. It's extremely important in chemistry, extremely important in determining whether the internal energy of something is high or low. And what I've left out is bonds. So bonding is a really huge deal. So I'm going to show you a little, I sent you a link to a little movie that I made that basically I have this PowerPoint. I think maybe I'll just go through the PowerPoint. Maybe that's better. So I made this PowerPoint when I know I have to share it, and I haven't done that yet, but I will. All right, I'm going to start new share. Here we go. All right, so do you see it? The Dr. Seuss thing? Yeah, so basically, I don't know how long ago it was, maybe 5 years ago or something like that. We had this vice president at Rhode Island College who used to at the end of every year, he'd have faculty get together and give little talks about a topic. So one time it was happiness, one time it was money, one time it was energy. So I never had any reason to talk about happiness or money. I mean, I didn't think I was an authority on any of those things, but I decided that, all of these non-science people I could imagine were going to talk about energy, energy, and I was like, I couldn't put up with that. So I thought at least somebody should actually give a talk on energy, like thermodynamics and stuff like that. So I thought, well, I'm talking to all these professors who've never studied science, a lot of them. So I thought I would make a PowerPoint, which I would call a child's introduction to the laws of thermodynamics. So I thought I would just show it to you. I'm just going to show you the beginning of it. It was actually it was longer than this, but I don't want to get too far ahead of myself. So I'm just going to show this to you. So I'm going to start the slideshow. Okay, so it's a child's introduction to, let's see. So any talk about energy starts with internal energy, okay? And that's because the first law has to do with it. So just like I just said, there's kinetic energy. If you have an atom, you have only translational kinetic energy, so that's a moving atom. If you have a molecule like a diatomic, it can also translate, but it can rotate, and it can also vibrate. I actually made these silly animations, which just makes me laugh because then my son became an animator and made fun of me, but anyway, whatever. Anything else? And really, bonding is so important that, I don't know, did you hear the sound effects? It sounds like energy is being released, but in fact, energy goes in, right? You need to supply energy to break a bond, okay? So it requires a large input of energy. And so if you took all the kinetic energy and all the translational kinetic, if it's a molecule, you could add in the rotation and the vibration and all this stuff. If you add it together, all of those contributions, it amounts to very small potatoes, very small, almost nothing. It's really not that significant. But if you think about the energy changes when you're breaking bonds, right? You have to go uphill to break a bond, or when you go downhill to make a bond, then that is, that's a really big deal. Those are big potatoes there, okay? So this is how I started to explain this to people who are not scientists. Anyway, I just thought it was funny. So then I went into how if you have two separated hydrogen atoms, that's a higher energy than two hydrogen atoms involved in a bond, and energy is released when you go to from two separated to two together. Let's see what I was going to say about that. So that means that the internal energy of two separated hydrogen atoms is actually greater than the internal energy of the molecule. It has a higher potential energy. Same thing with oxygen, except even more so, because the bond in oxygen is stronger. And so O2 is even more stable relative to the two separated O atoms than H2 is relative to two separated H atoms. So if you were going to put these guys, here's some H's and some O's separated versus as molecules, the separated atoms are higher in energy, right? So you might ask yourself the question, what else can you do with hydrogen and oxygen atoms? And of course, what you can do is make water. So where does water stack up on this internal energy scale? So if this is the difference in internal energy between the separated atoms and the diatomic molecules, water is down here, okay? Water is lower in energy than the molecules, the diatomics, and is much lower in energy than the separated atoms. So these separated atoms has the highest potential energy, and the water molecules has the lowest potential energy. So there's a giant change in internal energy if we're talking about going from separated atoms to water molecules. So basically, let's see, that would be the delta U if you went from H2, 2H2 plus O2 goes to 2H2O, at least in the gas phase. So what should happen when H2 molecules and O2 molecules react? It should release a lot of energy. And I have two nice videos that you could look at. The first one is showing a bunch of British guys exploding giant balloons. It's really kind of cool. But anyway, I'm not showing that now because you've probably all seen that before. I actually exploded a hydrogen balloon in that seminar. Anyway, so there's a big release of energy when these two guys react, unless you're smart and you harness it in a fuel cell or something like that, right? But anyway, if you want to know where did the energy go, is it lost? Well, according to the first law of thermodynamics, it is not lost. And there are only two places it can go. It could go into heat, or it could go into work. And this is something we're not there yet, but we're going to be there soon. But what I need to do is we can't sort of launch into molecules and making and breaking bonds yet, because we need to have a little fundamental, background in what we're talking about. So I think I'm going to go back to stop share screen, back to OneNote somewhere. Here it is. Okay, so I hope I convinced you the biggest contribution to changes in internal energy is from chemical reactions, okay? But we can't really leap into that yet. So we need to really pause. We can't get into, making and breaking bonds just yet. We will later. Because we have to look at simple situations first and understand them before moving on. What's going on here? Okay. All right. So first of all, I want to tell you once again that, we focus, at least at first, on the internal energy, the sum of all the potential, all the kinetic energies of this system. But we really cannot calculate it, right? It's really impossible to calculate U for a normal chemical system. It's just too hard. How can you count up all those things, all the intermolecular forces, all the everything? It's just, it's daunting task. There's too many contributing factors. It's just not possible. So we can do one simple calculation though. We can find U for a monatomic gas. In fact, we know this number already because we learned about it in the kinetic theory. Okay, so internal energy. So a monatomic gas has only translational kinetic energy, right? It has no rotation, no vibrations, it doesn't have a bond. It has no intermolecular forces. Gas molecules don't encounter each other. At least it's not at the critical point, so it doesn't have that. Let's consider it an ideal gas. Then we don't even have to worry about any of that. There are no bonds. And so the only thing it has is this translational kinetic energy. And we know what that equals. What is this? It's 3/2 RT, right? Because that's what came out of the kinetic theory. That is the kinetic energy, the average kinetic energy. So that's the internal energy, or the average internal energy, okay. So let's just say that the molar, this is for 1 mole, the molar internal energy for a monatomic ideal gas is 3/2 RT. Well, not quite. So a better way to write this, more correct, would be to say that the molar internal energy is equal to some value that it has, if the T is 0, plus 3/2 RT. So in other words, it has the part that depends on temperature, but certainly there are energies that molecule would have as it approaches absolute zero, like for example, like I said, nuclear or things like that, some internal atomic energies that we chemists really don't care about this. So chemists don't care. And since this is not a physics class, we just basically leave this out. And we just can think about it as being related to the temperature. So as the temperature goes up, molecules are moving faster, you have a greater internal energy. So at 25 degrees C, the molar, that's 298 Kelvin, the UM is equal to 3/2, 8.314 times 298, that's 3.7 kilojoules per mole. Okay, I changed it to kilojoules. So if all we cared about was helium atom floating around, we would know its average, what its internal energy was. But we don't just care about helium, right? We care about much more complicated systems. So really the bad news is we can't calculate U for any other system. That's the bad news. But the good news is we don't care. Or we don't want to. All we want is the change in the internal energy. And thermodynamics deals with changes in internal energy, but we want the change in internal energy, and we know a recipe for finding that. And that is actually, the recipe is called the first law. And it says that changes in the internal energy to the system equal the sum of the heat and work contributions. And if you don't understand that, that's fine, because we're going to spend some time dealing with that. Okay. Okay. So I don't know if I have enough time. I'm going to start this example. And my example is boiling a sample of water. Okay, so I just have a beaker of water, you know, and I have it, you know, here's a Bunsen burner or something underneath it, okay? And I have H2O in here, liquid. So my system, because we talk about the system and the surroundings, the system is the water in the beaker, okay? The surroundings would be the beaker, the flame, the atmosphere. Okay, we don't need to worry about, you know, what's happening in Arizona or something like that. Okay, it's really the close friends of the system, right? The things that are close to the system that could be affected by the system or would affect the system. So the question is, how does this water sample's internal energy change? So can we figure out the different things that are going to happen that are going to change the internal energy? So first of all, we know that the temperature is going to go up. And we know that temperature is related to the average kinetic energy. Right? We know that the average kinetic energy will go up because the temperature is going up. We have faster motion of those molecules. All of these translational, vibrational, and rotational motions all increase. Okay. What about the hydrogen bonding? What about intermolecular forces? Do you know why water has such a high heat capacity? So you know when you heat up substances, they don't all handle heat the same way. When you heat up water, the temperature of water does not go up that fast. If you put the same amount of heat into a block of iron, its temperature would go up much more rapidly than water would. And that's because of the hydrogen bonding in water. So when you add heat to liquid water and you have this network of hydrogen bonds, you know, and it's not regular. They're not like regular bonds, you know, it's sort of random. Well, it's not quite random because we have these delta negative and delta positives, okay? But we have a network of hydrogen bonds. And what the heat does is it gives it the energy to pull away from its, you know, to pull on those hydrogen bonds. So heat supplies the energy through kinetic energy of the molecules to pull on these hydrogen bonds and disrupt them, if not break them. Okay, and that's what sends molecules of water into the vapor phase, because they're not attached to their neighboring molecules anymore. So we're not breaking any real bonds, right? We're just breaking apart these intermolecular forces, and heat supplies the energy to do that. So the reason water has such a high heat capacity is because it has so many of these hydrogen bonds, and it is able to take in a lot of heat doing something other than moving faster, you know, and so the temperature doesn't go up as much. So this is why. So what's happening, of course, is we have our water here, and we have heat, Q, flows into the system. Okay? And let me finish the thought here. As you're separating these hydrogen bonds, you have it's like you're supplying energy to do that. So what you end up with are water molecules that have a higher potential energy than when they were all together, stabilized by multiple hydrogen bonds. So this heat supplies the energy to do this. Raises the temperature of the water, pull apart hydrogen bonds. And so we know that as this heat is going in, that the system ends up with an internal energy. The final internal energy is greater than the initial. Okay. We know that this UF minus UI, which is what we call the change in U, final minus initial, we know that that has to be positive. Okay. Heat's going in and it's raising the internal energy. The manifestations of that are breaking up hydrogen bonds, heating up the water, and something else is also happening, and that is that water in the liquid is going to water in the gas. Okay, and all of these, you end up with something with a greater internal energy than what you started. I think I have to probably end this because we have to get to lab, those of us who are going to lab. So I will continue on Wednesday. And I have to give out a quiz this week. I'll try to have it ready as soon as possible after Wednesday or on Wednesday, but I may not make it, maybe Thursday, maybe, we'll see. we will have a quiz that you'll have, you can do it over the weekend. Okay. All right, so I'll probably review this next time, and then we'll start in with the first law and how to calculate heat and work and all that stuff. Okay, good. I'll see you Wednesday, and probably some of you will see later. Bye.
Bye, that's really soon.
See you soon, some of you.